In this chapter, we will be looking at rational functions and equations. In this lesson, we will be reciprocating quadratic functions.
All right, hi everybody. So now we're going to take a look at reciprocal functions. We're doing the same thing as we did before here, but now we're going to look at functions that are quadratic when we take the reciprocal. Now, you're going to see a lot of the same things here that we did with the linear functions when we reciprocated them. Whenever we cross the x-axis, we're going to have an asymptote, except now, remember, a quadratic could possibly touch the x-axis twice, which means we can expect to have two vertical asymptotes. Additionally, remember that the action when we took the reciprocal of the linear function, the actions that it took, the directions that it moved, were always opposite to what the original function was doing. Well, because the quadratic or the parabola changes directions at one point, it's got this minimum value. When you take the reciprocal, a minimum is actually going to end up becoming a maximum. Okay, because when the parabola is dropping here, its reciprocal is going to want to go up, and the same sort of thing. So when it drops down to a minimum, the reciprocal is going to want to go up to a maximum. So anyway, so when it comes to reciprocating, this is what happens here. You simply take the entire function and make it 1 over that. So x squared minus 16, there's our quadratic. 1 over x squared minus 16 is our reciprocal. Same thing with x squared minus x minus 12. Now, how are we going to graph these things? Well, what we're going to do here is we're going to factor the denominator, and we're doing that specifically so that we can find the x-intercepts. Or, probably better stated, the vertical asymptotes, because the x-intercepts are going to become those vertical asymptotes, those places where the graph is undefined. Okay, then we're going to label the invariant points, okay, where y is either equal to 1 or negative 1. Now, we're probably not going to do much more than just that. It's only in special circumstances that we'd actually find those points. And then we're going to find the reciprocal of the vertex. And all we're going to do here is take the y-coordinate and flip it. Now, it's important that you remember that it's not the x-coordinate that we're reciprocating, it's the y-coordinate. Just so that you don't do too much work on that vertex and get it wrong because you overdid it. Let's take a look at an example. Okay, so for our first example here, we're going to take a look at the graph of y equals n is x squared minus 9. And we're going to sketch the reciprocal on top of this thing here. Now, I'm just going to draw the reciprocal right now, and then we'll answer some questions. We'll fill in this table here asking about the properties of both of these graphs here. But we should be able to draw the reciprocal right now without too much difficulty here. Okay, so first of all, I'm going to identify that those x-intercepts right there and there at negative 3 and 3, those are going to become our vertical asymptotes. And again, the reason for that is because the y-coordinate at the x-intercepts is 0. And when you remember, we are just reciprocating the y-coordinate. So when you reciprocate the 0, you get an undefined. So the graph is going to cease to exist there. So we're going to draw these dotted lines here. Additionally, we're going to identify where the graph goes through positive 1, where the original graph goes through positive 1 right there, and negative 1 right there, and right there. Okay? So those are our invariant points. Those 4 points are going to show up on the reciprocal graph as well. Now the last thing we want to do here is notice that our graph drops down here to negative 9. Now the vertex here is the point 0, negative 9. When we reciprocate that, that's going to become the point 0, negative 1/9. Now notice it doesn't become positive, it's still negative. Now it's really close to the x-axis, but it's still underneath. That minimum is going to become this maximum. Now let's think about how these things behave here. Now to start off with, we are going to ignore, I'm just going to grab a piece of paper here. We're going to ignore everything to the right of that asymptote because it doesn't matter. Things can change dramatically on either side of an asymptote. So as you read this graph left to right here, notice that the graph should be dropping down and it's approaching that x-intercept. Now our reciprocal takes really large values of y and makes them really small, and then takes really small values of y and makes them really big. So this thing swooping down to that x-intercept is going to is reciprocate into a function that swoops up towards the asymptote. So as you move, if you were going to move to the left, okay, moving to the left, my graph goes up, so my reciprocal's got to go down. It's not going to become negative. When you reciprocate positive y coordinates, you still get positive y coordinates, they're just fractions. And in this little section right here, when you reciprocate little positive fractions, you're going to get large values. Now let's take a look at what's going to happen in between the two asymptotes, and again, we're going to ignore what's out here. This graph starts from the x-axis and swoops down to an invariant point, down to a minimum. Okay, so now we're reciprocating these things. It's the exact opposite. Now we saw this the other day, that at an asymptote, the graph swoops off to an infinity. Now, because we are below the x-axis here, that's going to swoop up from negative infinity. It's going to come screaming up till it hits this invariant point, and then it's going to dramatically curve off here. And it's going to bend towards this maximum. Now this is a minimum point here. The vertex is a minimum, so the reciprocal is going to have a maximum up to there. Then the graph, the original graph, moves up to an invariant point. So our reciprocal is going to move down to an invariant point. Now my graph is not doing that justice, but you get the idea. It comes up and then comes back down. And then once I get to that invariant point, it goes up to the 0. So this is going to swoop down to negative infinity. Now it's really a really squared out sort of a graph here. The closer that vertex is up to the x-axis, the kind of the smoother that curve gets. The more you drag that down, the more pronounced that curve is going to be. It's going to be really dramatic. And then we look over here, we're going to ignore what's over on the left-hand side of that asymptote. We're going to start at 0, and it's going to, the original function swoops up through that invariant point up to infinity. So our reciprocal is going to come swooping down from infinity to the invariant point, and then it's going to ride along the x-axis because, again, the larger the y-coordinates get, the reciprocal gets smaller. They stay positive. So this right here, what you're seeing, a graph that looks something like this, that is a pretty standard way to draw the reciprocal of a quadratic. Now, it could change a little bit, but that's generally going to be what it looks like. Now, let's take a look at the different properties here. Okay, we're going to run through these guys right here. The domain of y equals x squared minus 9, that was the original. Well, the domain was all reals. Okay, there isn't a number out there that you couldn't square. There isn't a real number out there that you couldn't square and subtract 9 from. The range, we'll look back at what the original function looked like. It hit a minimum down here at the vertex 0, negative 9. So that means my range is going to be greater than or equal to negative 9. The x-intercepts we saw were negative 3 and positive 3. And the y-intercept, sorry, and I shouldn't say x equals, sorry. I should just say negative 3, positive 3. And the y-intercept there was negative 9. And then way down here, it had a local minimum. Now, our graph had a local min at the point 0, negative 9. That was the vertex. That's what it's asking for here. Now, when we reciprocate it. Well, when we reciprocate it, okay, the only points that disappear are the ones that had a y-coordinate of 0. Those points no longer count. That occurred at the x-intercepts. So what we're going to find here is our domain is that x cannot be negative 3 or positive 3. Both of those are no good. The range. Now, okay, here's a complicated one. It's going to take a little bit to kind of get used to. There are 3 distinct parts to this graph here. Okay, there's the left side of that asymptote. There is the right side of that asymptote. And then there's the graph in between those two asymptotes. Now, in between the two asymptotes, the graph moves down. The graph is going to shoot down to infinity. Okay, but from outside in, the graph comes screaming up to a maximum of negative 1/9. That's the maximum. So there's a part of this graph that's going to be less than or equal to negative, oops, I was going to write negative 9 there, but it's negative 1/9. But there's another part of this graph, and that's the parts that are out here. Now, both of these are going to have the same range. They come down from positive infinity, and they ride along the x-axis, but they never actually get to it. They never actually touch where that y-coordinate would be 0. So every point along those two curves there is going to have a y-coordinate greater, whoops, man, I'm having a hard time, greater than 0, not or equal to, just greater than 0. Here, this is going to be or equal to negative 1/9 because it actually does get to a maximum vertex there, 0 comma negative 1/9. But the other part of that graph isn't going to get to the 0. Now, x-intercepts, well, we just said here, it doesn't actually touch the x-axis. The y-intercept, well, in the original graph, the y-intercept was negative 9, and so you reciprocate that y-coordinate, so negative 1/9. Our vertical asymptotes are going to be where the domain has problems, so x is equal to negative 3, x is equal to positive 3. Those are our two lines. The next question it's asking for is the horizontal asymptote, and this doesn't change much from what it was before. It's going to be still the x-axis. That will change in a later course, just not this one. The invariant points. Okay, well, to find the invariant points, what we got to do is set our graph equal to 1 or negative 1 and figure out what the x-coordinates are. Now, I suspect that the original intention of this question is just to identify how many there are. But let's figure out what those points are anyway. And let's use the original graph, not the reciprocal, because the original one's going to be easier to use. So if we let y equal 1, add 9 to both sides, we're going to get the square root of 10. So we're going to get 2 points here, positive and negative root 10, and then the y-coordinate's going to be 1. Or we let the y-coordinate go to negative 1. So when I bring that 9 over, I'm going to get 8. When I square root the 8, I'm going to get a number that can be simplified. Okay, it'll be plus or minus root 8 equals x, which is the same as positive or negative 2 root 2. And that implies the 2 points, positive and negative 2 root 2, comma negative 1. So down here, our invariant points will be positive negative root 10, comma 1, or positive and negative 2 root 2, comma negative 1. So we got 4 invariant points, and we saw that before here. Now in this case, what happened to, where's the local max here? Well, we've already seen that local min in the previous became a local max in this one, and that y-coordinate there was negative 1/9. X-coordinate stays the same, y-coordinate gets reciprocated. Okay, there you go. All right, let's take a look at another problem. Here, we're going to take the reciprocal of negative x squared minus 4x plus 12. Okay, but we're not going to give you what the graph looks like, so we got to go through the process of graphing this thing first here. Now, just some things right off the bat that should be pretty straightforward. This is going to have a y-intercept of positive 12, so I know it's going to go through there, which means I already know what the y-intercept of the reciprocal is going to be. It's going to be positive 1/12. Now, what I want to do here is, well, a couple things here. First of all, I'm going to factor out the negative. Okay, and then what we're going to do here is we're going to factor this. So factors of negative 12 that add to 4, well, we're going to get positive 6 and negative 2. And so we're going to get x-intercepts at negative 6 and positive 2. So x-intercept here at negative 6, x-intercept there at positive 2. Okay. Now, I'm going to complete the square so I can get the vertex. So I'm going to take out the negative x squared plus 4x. Half of 4 is going to be 2. 2 squared is 4, so I'm going to add 4 and subtract 4. Then I had that plus 12 hanging out there. When I complete the square, I don't need the negative one there, so I'm going to multiply that by a negative. So take out a positive 4. And then that's going to factor down to get, whoops, I have no idea why I wrote a y there. It's not like I was going to write it again. X plus 2 squared plus 16. So my vertex is going to be the point negative 2 comma 16. So negative 2 comma 16 right there. I've got the y-intercept. I've got the two x-intercepts. So this thing is going to look, actually it's going to be symmetric, so it's going to go right through there. So it's going to go down. That's not going as nicely as I would have liked. There we go. There we go. So there's our parabola. Okay, there's the original. Now we're going to draw its reciprocal. So I see that it goes through x-intercepts here at -6 and +2. So I'm going to draw my asymptotes through there. A vertical asymptote through there. So it's going to be x equals -6, x equals 2. I'm going to have an invariant point there and an invariant point there. Oops, sorry, not there and there. My mistake. Sorry, that's going up by 2, so it's actually going to be a little bit closer. Ooh, it's going to be really tight. This comes down. It's going to be right in there. Right in there, right in there. It's going to be a little hard to draw, but that's okay. Now, this maximum here at -2, 16 is going to become a minimum -2, 1/16. Now that's going to get really close to the x-axis there. It's going to be a little hard to draw. But, same sort of thing. We're going to start on this side of that asymptote. Notice that my graph is below the x-axis here. When you reciprocate it, it's going to come along the x-axis down to the invariant point, which I've drawn a little too far over, and then it's going to ride down the asymptote there real close. Over on this side, it's going to do something very, very similar. It's going to come riding along the x-axis down to the invariant point, and then it's going to ride along that asymptote. Okay, and that's because the original function in both of those spots there is moving away. Okay, as you move away from the vertex, like you go to the right or to the left, the original function is moving away from the x-axis, so the reciprocal is going to be moving towards the x-axis. In between the two, my graph on both cases here starts at 0, the original, and goes up to a maximum. So my reciprocal is going to start up at infinity, it's going to come screaming down, hit the invariant point, and then it's going to curve down to this invariant point, which is then going to come up. It's going to hit 1/12 there. Okay, that's going to be my y-intercept. It's going to curve up, hit that invariant point, and then, whoops, and then it's going to ride up along, okay, ride up along that asymptote. So here's another way that this graph could look. You'll see on the previous page when we did this in the other example, it was just the reciprocal, or sorry, not reciprocal, the flip of that. Okay, so there's our reciprocal there, curves down, and then this one curves. It's quite dramatic when it gets down to here, right? And again, the further away that vertex moves from the x-axis, the more this is going to square out. Okay, the more dramatic that curvature is going to be. All right, let's take a look at the properties here, the domain. For the original, again, it was just a regular old quadratic, so x is an element of the reals. The range, well, this parabola opened down from a maximum of 16, so it's going to be less than or equal to 16. The x-intercepts, we'd already determined those. The x-intercepts we knew were -6 and +2. And the y-intercept we discovered was 12. And then going down here, this thing had a max point at the point -2, 16. So now let's take a look at the same properties but with the reciprocal. What was the domain? Well, okay, those x-intercepts there became those gaps, okay? And so right now I can write that the domain here is going to be that x cannot equal -6 or +2. Those are the two spots that were the x-intercepts in the previous graph. Those lead to holes in the graph. My range, oh, okay, the range is a little bit more complicated. Now here, notice these two curves here are basically just mirror images of each other. They're doing the same thing. They come up to 0, but they don't get there. Okay, they get closer and closer and closer, but they never actually get to 0. But when they come close to the vertical asymptotes, these things swoop down and they drop infinitely. So part of this range is going to be that could be less than 0. Now, we have to take into account what's going on between the two asymptotes. And in this case, this thing starts way up at infinity and then drops down through the invariant point, and then it goes down to a minimum. Okay, and I know that's not 100% clear here, but that is the vertex 2, negative 2, 1/16. And so our graph here is going to be greater than or equal to 1/16. Okay. X-intercepts, well, the reciprocal doesn't have any. It doesn't hit the x-axis. The y-intercept is going to be the reciprocal of the one that we had originally, so 1/12. Okay, vertical asymptotes. These are related to the gaps in the domain. So x is equal to 6, x is equal to 2. Horizontal asymptote comes up over and over again. Y is equal to 0. All right, the invariant points. Let's take a look at what the invariant points are going to be. Okay, so we're going to come up here. Maybe I'll erase this little bit of a work here, and so we can put rest of our work. So I'm going to start with the original function here to find our invariant points, because it's going to be just a little bit easier to work with than the reciprocal, and the results will be the same. So I'm going to start off with 1 in there. And I'm actually going to bring everything, because the x squared is negative, you're going to bring everything over to the left-hand side. So it'll be x squared plus 5x. I'm going to subtract 12 minus 11 is equal to 0. Well, the factors of 11 are 11 and 1. Those aren't going to combine to get you 5. So I'm going to have to use the quadratic formula to figure out what that x coordinate is supposed to be. So that'll be negative 5 plus or minus the square root of, now let's see if we can do this a little bit faster than we've done it in the past. 5 squared, okay, so 25, minus 4 times a times c. So minus 4 times 1 is negative 4, times negative 11 is going to be positive 44. So 25 plus 44, 69. And then the denominator will be 2 times a, or 2. Now, 69, the factors of 69 are going to be 3 and 23. So I'm not going to be able to simplify that. That is as good as it's going to get. And so on one hand, the set of invariant points that I've got will be negative 5, and here's the two of them, plus or minus the square root of 69 over 2, comma, positive 1. Okay, so there's one set of invariant points. Now, let's take a look at what happens if it was equal to negative 1 instead. So I get negative x squared minus 4x plus 12. Same thing, I'm going to bring everything over to the left-hand side. So x squared plus 5x. This time, though, when I bring the 12 over, I'll subtract it, and I'll get negative 13 equals 0. But we're running into a similar sort of problem here. 13, its only factors are going to be 1 and 13. And those aren't going to combine to give you 5. So again, I'm going to jump to my quadratic formula, which will be negative 5 plus or minus the square root of, okay, 5 squared is going to be 25, minus 4 times a times c. So again, it's really, the issue here is the negative 4 times that negative 13. Excuse me, 4 times 13 is going to get you 52. So it'll be 25 plus 52. You got to love that. 25 plus 52, that's just going to be 77, all over 2. And again, I can't simplify that. So the points that I'm going to get here will be negative 5 plus or minus the square root of 77 over 2, comma, negative 1. Okay, and so those are our invariant points. Now, I'll write those down here real quick. So we get negative, whoops, I want to make sure that that negative is clearly with just the 5 there. So negative 5 plus or minus root 69 over 2, comma 1. The other two are going to be negative 5 plus or minus root 77 over 2, comma negative 1. Now, finally, the vertex. The vertex on the original was negative 2/16, so our reciprocal will be negative 2, comma 1/16. We're just going to flip that value. And because the original one was a maximum, this one is going to become a minimum. Okay, So in the last couple questions, we did a lot of work to come up with the reciprocal and then all the different properties. Here, we just want to get used to the idea of sketching these things. So let's just take a quick look. Again, first thing I want to do is I'm going to identify those vertical asymptotes, and that's where the x-intercepts are in the original. It's going to be a little harder to see here because it's right along the y-axis. And then our invariant points where the graph goes through 1 or -1. And then here, our vertex, our minimum, -2, -4 is going to become that maximum -2, -1/4. Remember, it's the y-coordinate, not the x-coordinate that we're reciprocating. Now, the parabola opens up, so these two outer pieces are going to swing down and ride along the x-axis, like that. This one down here, this is the part that's got the minimum to it, so the reciprocal here is going to come up, go through a maximum, and then come back down. Okay, so this one has got this shape right here, sort of like that. This one, okay, again, this is going to be a little bit clearer because the x-intercepts here aren't on the y-axis. It's going to be a little bit easier to see those asymptotes. Additionally, here's our 1 and 1, -1, -1, the y-coordinates. Now, this one had a maximum of 0, 3. So the reciprocal is going to have a minimum of 0, 1/3. Now let's deal with the part that's outside of the asymptotes because we know that those are going to look the same. Those are going to ride along the x-axis and then swing down, ride along the x-axis and swing down. And then what's inside here, this is the part that's got the maximum, so that's the part that when you reciprocate it, will end up having the minimum. Okay? And so in this case, again, my reciprocal looks like that. Okay, it's got those three pieces there. And hopefully that kind of gives you a better sense of how to approach these things in general. Okay? When it opens up, it's going to have a shape more like that. If it opens down, it's going to look more like that. All right. Now, in this case here, we've got a couple questions. What we're going to do is we're going to sketch the graphs of y equals f of x, y equals 1 over f of x. We're going to do it on the same axes, and then we're going to identify the different pieces here. We're going to get the equation, and then the asymptotes and invariant points and intercepts. Okay, so we're going to start off with y is equal to x plus 3. Okay, so y is equal to x plus 3. It's got a slope of 1 and a y-intercept of 3. So it's going to go through here and with a slope of 1. Okay, it's just going to go up 1 over 1. And away we go like that. So it's going to slide along like that. Now, I know that when I take the reciprocal of it, it's going to have an asymptote right here. Whoops. Okay, it's going to have an asymptote right there through the x-intercept. I know it's going to have an invariant point here and an invariant point here. And actually, those are nice and easy to read off of the graph. It's going up like this, and so if you think back to what the linear ones look like, when you approach the asymptote, when the original one approaches the asymptote, or that x-intercept, the reciprocal is going to be riding along that vertical asymptote. It comes down, goes through the invariant point, and then along the x-axis. Just like here, this is going to come up from the x-axis, hit that invariant point, and then start screaming down here. So that's what the reciprocal is going to look like. Now, the equation is going to look like this. It's going to be y equals 1 over x plus 3. That's easy. We've already seen that it had a vertical asymptote, I should say, at x equals -3. But it also had a horizontal one at y equals 0. And almost every one of the ones that we're going to do, they're going to end up looking like that. The invariant points we could read right off the graph. That was -2, 1, -4, -1. Those turned out to be pretty easy. They're not always so simple. The intercepts, well, there's no x-intercept. The y-intercept, the original one was +3, so the reciprocal here is going to go through 1/3 necessarily. Okay, has to go through that. Okay, let's try the next one. In this next one here, we're looking at y equals x squared plus x minus 6. Now, we're going to do a couple things to this. First of all, let's factor that. So that's going to be x plus 3, x minus 2. Now, meaning that I'm going to get x-intercepts here at negative 3 and positive 2. So negative 3, positive 2, which, by the way, already tells me I know what the vertical asymptotes are. In fact, we might as well go down here and write that. I already know the vertical ones are going to be x equals negative 3, x equals 2. And for that matter, I already know it's going to have a horizontal asymptote at y equals 0. Okay. Now, that's not always true, just like this isn't always true. It's just that for the vast majority of the questions that we're going to do in this course, it will be true. Okay? Now, the next thing that I want to do is I'm going to complete the square on this to figure out what the vertex is. Oh, by the way, I also know from here that the y-intercept here is going to be negative 6. Okay, so the original one is going to have a y-intercept here of negative 6. Now, that also tells me that the y-intercept is going to be negative 1/6. I know it's going to be the reciprocal of that. And I already know there's going to be no x-intercepts. Since we started this, none of the questions have ever had an x-intercept. So there's no reason to suspect that this is going to be any different. Okay. In fact, there's no x-intercepts because we already know that there's a horizontal asymptote at the x-axis. It's not going to touch it. Anyway, let's keep going here. So let's complete the square. So y is equal to x squared plus x minus 6. So what I'm going to do here is take that middle term there, that 1x, divide that by 2. So it'll be 1/4 minus 1/4, whoops, minus 6. So y is equal to x squared plus x plus 1/4. We're going to take the negative 1/4 out. So y is going to be equal to x plus 1/2 squared minus 25 over 4. Now, those are sort of awkward numbers, but the vertex is therefore going to be 0.5, or sorry, negative 0.5, comma, and what's that going to be? Well, negative 25 over 4 is going to be negative 6.25. So when I put those on my graph here, it's going to be negative 0.5 here. It's going to be just slightly lower than that. A little bit of symmetry there puts it there, so it's going to come up. It's going to come up. There we go. Now, let's draw the reciprocal. It's going to go through the x-intercepts. Okay, it's going to go through points where the graph goes through 1 and negative, 1 and negative 1, 1 and negative 1. That's a little tough there. They're quite close. Okay. We know that this part right here, just because we've done enough of these, is going to come down and swing down. This is going to come down, swing down. Since this part in between the asymptotes has the minimum, it's going to go up here to negative 1/6. The reciprocal is going to have that maximum, so it comes up from negative infinity through the invariant points to the maximum and back down again. All right, our function is going to be y is equal to 1 over x squared plus x minus 6. Now, to figure out what our invariant points are, we're very likely going to have to use our quadratic formula. So first of all, let's go over here. Let's do a little bit of work here. Let's set x squared plus x minus 6. Let's start with it equal to 1. So bring the 1 over x squared plus x minus 7 is equal to 0. Okay. Which means our x-intercept here is going to be negative 1 plus or minus the square root of, now this is going to be 1 squared, or 1, minus 4 times a times c. Well, negative 4 times negative 7 is going to be positive 28, plus the 1 there is going to be 29 over 2, 2 times 1. Okay, well I'm not going to be able to simplify that root 29, so that means invariant points, we're going to have negative 1 plus or minus root 29 over 2, comma 1. Now that's just one set of invariant points. The other set comes if I set x squared plus x minus 6 equal to negative 1. Okay. Now, add that to both sides. I'm going to get x squared plus x minus 5 is equal to 0. And again, I'm not going to be able to factor that. So x is going to equal negative 1 plus or minus the square root of, and now we're going to do this again, 1 squared, it's just going to be 1, minus 4 times a times c. So minus 4 times negative 5 is going to be positive 20, plus that 1 is going to be 21 over 2. And again, whoops, sorry, can't see that. I'm not going to be able to simplify that root 21. So my other set of invariant points are going to be negative 1 plus or minus the square root of 21 over 2. I'll have to erase this, comma, negative 1. Okay, so those are invariant points. We already figured out what the intercepts were going to be. That's what it's going to look like. So just pay attention to really this is what the linear one's going to look like. It's going to have these two curves to it. Now, if it has negative slope, those are going to be in a different location. And if it's parabola, now granted, if you experiment with this on your own, you're going to find that you can actually get different shapes. But this is typically how we want you to approach this, and we're going to test you on this. Either it's going to have these two branches up top and this guy below, or it's going to be the flip of that.